Okay, welcome everyone. Today, Stephen will tell us about total positivity.
All right, thanks very much for the introduction and the invitation. I'm very happy to speak to you here. So I decided to split my talk into two parts. The first will be an introduction, which is positivity, and the second part will be more higher level research talk on an application to Schubert calculus. But in the first part, I wanted to kind of motivate why, at least I think, total positivity is an interesting subject, and it's kind of hard to explain briefly what it is. I mean, it's just, total positivity is just looking at spaces and their positive parts, but that doesn't indicate why it should be interesting. And I think it just turns out again and again in examples that considering positivity leads to interesting results and insights. So I want to kind of try to justify that through examples. So I just want to start with maybe a kind of couple of results that predate the history of total positivity. So the first has to do with sign variation. So if I have a vector v in Rn, I'm going to find var of v to be its number of sign changes, just viewed as a sequence of numbers and just ignoring the zeros. So here I would have a sign change from 3 to -1, and I have another sign change from -3 to 7. So I have two sign changes. And Descartes in the 1600s proved this result, that if we have a non-zero polynomial with real coefficients, then its number of zeros on the positive real line is bounded by the number of sign changes of its sequence of coefficients. So sign variation and actually this result will turn out to come up later. The second result from the early 1900s, called the Perron-Frobenius theorem, is about positive matrices. So square matrices with positive entries says that such matrices have a positive eigenvalue lambda, which is strictly bigger in magnitude than all other eigenvalues, and it's simple. So it has a one-dimensional eigenspace, and its eigenvector can be chosen to have positive entries. So for example, here I have this randomly chosen positive matrix. Here is the Perron eigenvalue, and this is a corresponding eigenvector, which has positive entries. This result is of course, very important in the theory of Markov chains, and it also will come up for us. Okay, so the theory of total positivity kind of developed concurrently by two groups, and the first time it developed was through work of Kellogg starting in the 1910s. And Kellogg was interested in orthogonal polynomials, and this is from the introduction to his first paper on the subject. And he observes that orthogonal polynomials often have the property that each one changes sign in the interior of orthogonality once more than its predecessor. And he says this is so universal, these systems are often called oscillating functions. And he asks, does this oscillation property follow from orthogonality? And the answer is no. He gives a simple counterexample. And then he shows that oscillation is a function of total positivity. So he introduces total positivity for kernels. So a kernel is just a continuous function of two variables. Here I'm going to restrict my variables to lie in the unit interval. And so just a real value continuous function. And how you can think of it is like a continuous analog of a matrix. And the continuous analog of a vector is just a real valued function on the unit interval. And so our kernel is going to act on functions. So the kernel k times the function f is another function, which we just get by integrating k times f with respect to the second variable.
Why do we call it the kernel?
I actually don't know.
I never learned.
Yeah, I think kernel just means like the core of something. So it's I don't think it has to do with like the null, the zero set of a transformation. But yeah, I don't know. Good question. Are there other? Yeah, if there are questions, please interrupt. Okay, so we call a kernel totally positive if for all n, positive integers n, this n by n determinant is positive. So here I've chosen n strictly increasing x variables, n strictly increasing y variables, and I take the determinant of the matrix K of xi, yj. And an example of this is e to the xy. Can show is a totally positive kernel.
There's a typo there, right? X. One, Y, N.
Yes, thank you. Very good. Okay, so what Kellogg proved for symmetric kernels, and then Gottmacher generalized it to non-symmetric kernels, is if we have a totally positive kernel, then its eigenvalues are positive and distinct. So you know, say that f is an eigenvector if kf is lambda times f, and then lambda would be an eigenvalue. And so these eigenvalues are all positive and distinct. And if fi is an eigenfunction corresponding to lambda I, then fi has exactly k minus 1 zeros on the unit interval, and the zeros of consecutive eigenfunctions interlace. So this is the oscillation property. And how this has to do with orthogonal polynomials is if k is symmetric, then these eigenfunctions will be mutually orthogonal.
There's another typo in the domain of K.
Squared.
Thank you. Okay. So I just want to point out here that in the continuous case, positivity is basically a consequence of non-vanishing. So if this determinant is always non-zero, then by the intermediate value theorem, it has to be always positive or always negative. And so this positivity is actually equivalent to saying these determinants are non-zero and positive somewhere. And what's kind of surprising is that in the discrete case, you know, we don't have the intermediate value theorem, but still total positivity seems to lead to interesting consequences. So after this, Gottmacher, you know, saw Kellogg's work, and as I said, he generalized it to the non-symmetric case, and he also, with his advisor Crane, generalized it to matrices. So a matrix is called totally positive if all of its minors are positive. So every square submatrix has a positive determinant. So like this minor here is a 2 by 2 minor, which is 3. And you can check that this is a totally positive matrix. And Gottmacher and Crane proved the discrete analog of the result on the previous slide. So if we have a square totally positive matrix, and eigenvalues over the complex numbers are positive distinct real numbers. And if Vi is the eigenvector corresponding to lambda I, then VK has k minus 1 sign changes. And the positions of the sign changes of consecutive eigenvectors interlace. And so here, we're kind of thinking of sign changes as a discrete analog of zeros of a function. And that's basically because, you know, we're kind of thinking of our sequence, like we're thinking of vector and Rn as a sequence of values that we've sampled from a continuous function. And by the intermediate value theorem, if a continuous function changes sign between two values, it would have to have a zero in between. So that's the idea here. So in this example, here are my 3 eigenvalues, and here are the 3 eigenvectors, and you can see the first one does not change sign, the second one changes sign once, and the third one changes sign twice. I won't go into detail on the proof, but I just want to say the idea is the following. So we consider A acting on this exterior power, the kth exterior power of Rn. So this is a n choose k dimensional vector space, and then we can think of the action of A as a big n choose k by n choose k matrix. And the entries of that matrix in the standard basis of this exterior power are precisely the k by k minors. And so saying A is totally positive means that these, this big matrix has positive entries in each of these exterior powers. And so we can apply the Perron-Frobenius theorem. And it turns out, okay, there's still some more work to do, but that's the general idea. And also this is going to come back later when we want to generalize this to other algebraic groups. Okay. I just want to also point out this nice result of Kotulyansky, who was another student of Crane, which is that if we're only interested in part one, the eigenvalues being positive and distinct, we don't need all the minors to be positive. We only need the principal and almost principal minors to be positive. So these are minors where the row subset and the column subset we choose differ by at most one element. And there are matrices that satisfy this condition, but are not totally positive. Okay, so that was kind of one development, one line of work on total positivity, and kind of the other line of work arose out of work of Schönberg. And Schönberg was trying to answer a question of Polya. Polya's question was, which linear maps from Rm to Rn weakly diminish sign variation? So the sign variation of A times V is less than or equal to the sign variation of V for all V in the domain. And again, his motivation was thinking of sign variation as a discrete analog of the number of zeros of a continuous function. And so this is asking which linear transformations, weakly diminish the number of zeros, but in the discrete setting. And Schönberg showed that if A is injective, then, we can view A as a matrix, and then it satisfies Polya's condition if and only if, for all k, the non-zero k by k minors are all positive or all negative. So, for example, here I have a matrix, so the 1 by 1 minors are all positive. The 2 by 2 minors, you can check they're all 0 or negative. And the 3 by 3 minors are all 0 or positive. So this satisfies Schönberg's condition. And just to mention that Motzkin in his PhD thesis solved this problem for non-injective transformations as well. And Schönberg and his students and collaborators went on to prove a lot of important results in this area. So one of them is due to, it's called the Ising-Schönberg-Whitney theorem, which is about real-rooted polynomials. So let's suppose we have a polynomial, f of x here, which is normalized so that some coefficient is positive. And then we want to know when are all the complex zeros of f real and non-positive. And they show this holds if and only if this infinite matrix is totally non-negative, meaning all its finite square submatrices have non-negative determinant. And this is called a triplets matrix because it has its constant along translates of the main diagonal. Okay. Let me just mention there's also a generalization from polynomials to power series, but then it's a bit more delicate to state what it means to have this zeros property. So this was the result of Edray at the same time. And I just want to mention that Edray's result can be used to formulate the Riemann hypothesis. That's just the statement that a certain triplets matrix is totally non-negative. And it's the triplets matrix associated to this power series where psi is the Riemann psi function. And so the idea, the idea here is not very deep. It's just the Riemann hypothesis is saying the non-trivial zeros of the zeta function lie on the critical line. And so you can get rid of the trivial zeros with the gamma function. And then you can just rotate the critical line so it becomes the real line. And then you use the square root to kind of turn the positive zeros into the negative zeros. So
For a complex zero to be non-positive.
I just mean they're real and not positive. So they're negative or zero.
I think the project's the last.
Yeah. So yeah, so I'm not sure exactly what to make of this. Maybe this means one should use total positivity to prove the Riemann hypothesis. Or maybe it indicates that proving results in total positivity can be hard. I also want to mention that I know people here are interested in log concavity. So saying the 2 by 2 minors are non-negative means that the coefficients are non-negative and form a log concave sequence. And that's basically if and only up to some degenerate cases. So looking at higher order minors, you can think of as a higher order generalization of log concavity. Another question you might ask is, we have an infinite matrix here, but do I need to actually check infinitely many minors for this theorem? And it turns out that actually you do. And Schoenberg has this beautiful result which proves one direction of the theorem, which says that if we fix K and all we know is that the K by K minors are non-negative, then all that tells us is that F is non-zero in some sector, which is symmetric around the positive real axis. And this sector, the bound here is tight, so this sector can't be enlarged. And so what's going on here is that as the minors get bigger, so as K goes to infinity, this sector will widen and actually encompass the whole complex plane except for the negative real axis. But for example, if all we know is the 2 by 2 minors are non-negative, this only tells us that our function is non-zero on a small sector.
Does the 2 by 2 minors being non-negative imply the 1 by 1?
I mean, basically, so if I know, for example, A0 is positive, then there's a 2 by 2 minor, which is A0 times AJ. And that would tell me AJ is non-negative.
So the statement is correct that you don't need to assume A less.
Yeah, it implies the smaller order minors, actually. Yeah. Good question. Okay. Another nice thing Whitney did, who was a student of Schoenberg, was she found an efficient algorithm to test whether a matrix is totally non-negative. So a matrix is just totally non-negative if its minors are greater than or equal to 0.
Is that the same Whitney that we know?
Like Hassler Whitney?
Yeah.
No, this is like Anne Whitney. So I think she left academia soon after her PhD. Yeah, but she was a student of Schoenberg. A matrix has exponentially many minors to check. So, and to test for something, we don't want to do something in exponential time. And Whitney actually found that there's a nice algorithm that runs in cubic time for testing for total non-negativity and total positivity. And the idea is that if I have a matrix that's totally non-negative, and I take a row and I add a positive scalar multiple to an adjacent row, then that preserves total non-negativity. And the same for adjacent positive column operations. And Whitney's algorithm basically reverses this idea. So she takes a row, and then rather than adding a positive scalar multiple to an adjacent row, she has a negative scalar multiple until one of the minors becomes 0. And then you repeatedly do this until you either get an error or you get to the 0 matrix. This is also known as Neville elimination in the literature. Another nice consequence of this, which was, it's often called the Loevner-Whitney theorem because it's in a paper of Loevner, but he just observes it follows kind of directly from Whitney's algorithm, which is a explicit parametrization of all totally positive n by n matrices. So this is the parametrization where these stars are positive real numbers. So I have n squared stars here. So in the middle here, I just have a diagonal matrix with positive diagonal entries. And then here are some x's and y's. So x sub I is just this matrix I get from the identity matrix by putting a t in row I and column I plus 1. And yi is the transpose of that. And so, for example, multiplying on the left by xi or yi is these adjacent row operations. And multiplying on the right is adjacent column operations. And so then what we do is we take reduced words for the longest element in the symmetric group Sn. And so on the left here, I have the reduced word in the y's, and then on the right, I have the reduced word in the x's. So for example, for n equals 3, this could be our parametrization. So here's my diagonal matrix, here's the product of y's, and here's the product of x's. Okay. Now, if you were interested in generalizing this, okay, if you want to view, this is about the symmetric group and GLN, so this is a type A story. If you're interested in generalizing this to other types, it's kind of very clear what you should do here. But strangely enough, this was not done until the 90s by Lusztig. So what Lusztig did was he basically used this Loevner's-Whitney theorem to define the totally positive part of an arbitrary split real reductive algebraic group G. So what we do is we fix the set of simple roots I and take a pinning. So that basically means we fix two opposite Borels, B and B minus. T is the maximal torus, which is their intersection. And then we have these xi's and yi's. So for each simple root little I, we take an embedding of SL2 inside our group, and then xi and yi are given as on the previous slide. Okay, so if you don't know what this means, that's okay. But the point is everything generalizes very naturally. So then Lusztig defines the totally non-negative part of G to be the semi-group. So this is like a group, but not with inverses necessarily. And it's generated by the xi's and yi's with positive parameters and the positive part of the torus.
Is it clear from the definition that G non-negative is closed?
That's a good question. Yeah, I guess so, because it's a semi-group, I think. So by definition, you can just multiply stuff. Yeah, maybe.
Image of the multiplication map of some groups. Some theorem that says.
Oh, you mean topologically closed?
Yeah, like compact.
Oh, yeah, sorry. No, maybe not. It's certainly not compact. It's closed, but it's not like bounded, for example, in general.
There's a general theorem that says if you have an image of the multiplication map of algebraic groups, it's closed.
Okay. Interesting.
Image of the multiplication of the positive part, then this is like a part of them.
That I don't know, but it seems like you might be able to.
Yeah, that's a good question. I'm not sure the easiest way to prove it, but at least Lusztig does prove that it is the closure in the Euclidean topology of the positive part. By the way, I also didn't define the positive part of the torus, but okay, there's a natural way to do that. Okay, and the positive part is just defined, you just do Loevner's theorem, except now, we choose a reduced word for the longest element. Okay, and then Lusztig wanted to generalize the Gottmacher-Crane theorem that every totally positive matrix has positive eigenvalues, and the analog of that statement is that every totally positive element of big G is conjugate to an element of the positive torus. And his proof Yeah, so actually, so how Lusztig got into this was he was introduced what's called the canonical basis for a quantum group. And these turned out to have some special positivity properties. And Bert Costant, who knew about this classical theory of total positivity, he asked Lusztig, if the canonical bases are related to that stuff. And so how Lusztig proves this theorem is actually using his theory of canonical bases. And it kind of generalizes the theory from before. So before we were considering matrices acting on exterior powers. Now we consider little g acting on irreducible G modules V lambda, associated to dominant characters lambda. And we take the canonical basis of V lambda, and Lusztig shows that if this little g is totally positive, then the action on this V lambda has positive entries, and so we can apply the Perron-Frobenius theorem. So this is quite, it's the proof uses, because this canonical basis is quite complicated. Okay, so you might also ask, so for totally positive matrices, we can describe them as matrices whose minors are all positive, and do we have a similar description of the totally positive part of G? And that was worked out by Fomin and Zelevinsky, who characterized the positive and non-negative part of G by what are called generalized minors. Okay, and this work led them to develop the theory of cluster algebras. I maybe won't say what cluster algebras are, so if you haven't seen them, then you can maybe take this as a brief introduction to the idea. But this arose out of the theory of total positivity. And what they were studying was these total positivity tests. And there's different spaces you can use to motivate this. I'm going to work with this set U sub n of upper triangular n by n matrices with ones on the diagonal, so unipotent. And the totally positive part is just the subset where all minors, which are not trivially zero, are positive. So for example, like this 1 by 1 minor in the bottom left corner is trivially zero. So I'm going to ignore that. But like this 2 by 2 minor in the top right is AC minus B. So I'm going to require AC minus B. It's positive. Okay. And we have this nice classical result, which follows from work of Cryer and appears more explicitly in Gasca and Peña, that we don't have to test for total positivity here. We don't have to test all the minors. We only have to check the contiguous topmost minors. So minors which use consecutive subset of columns and a top justified subset of rows. So for example, we have to check all the entries in the first row. So we need to know 1, A, and B are positive. And I need to know this 2 by 2 minor is positive, which is just 1, and this 2 by 2 minor, which is AC minus B. But in particular, I don't need to check C. And this makes sense because if I know A, B, and AC minus B are positive, that implies C is positive. Okay, and as I said, this is a classical result, but Berenstein, Fomin, and Zelevinsky found this beautiful proof using wiring diagrams. So a wiring diagram is just a picture of wires. So on the left, I label my wires 1, 2, 3 from bottom to top. And then on the right, they're supposed to switch order. So they're supposed to be 3, 2, 1 from bottom to top. And each wire is supposed to cross exactly once. So this is saying that if I look at the pattern of crosses, this should form a reduced word for the longest word in the symmetric group. So here would be S1, S2, S1. And then each chamber I label by the wires passing below it. So this chamber I'm going to label 2, 3, because 2 and 3 are the wires passing below it. And this corresponds to the minor 2, 3, which means I look in columns 2 and 3 and take the first 2 rows. So this minor would be AC minus B. Okay. And if you notice, well, okay, these 2 are 1, but the other minors are the minors in my positivity test. And I want to know if these minors are positive, that all the other minors are positive. And the way they prove this is doing braid moves. So here, I can do a braid move, which would get me to this wiring diagram. And if I do that, the only chamber whose label changes is this one. And it changes from being labeled by 2 to be labeled by 1, 3. And the minor labeled by 1, 3 is C. And it turns out that whenever we do a braid move, we have a positive exchange relation. So we have this equation with no minus signs. And here, this is A and this is C. So if I know everything in this equation is positive, except one of these two terms, then I know the other term is positive. And so if I know these minors are positive, then so is this one. And what Berenstein, Femina, Zelevinsky argue is that doing braid moves, starting from this wire diagram, then you can get every minor appearing. So that tells you all the other minors are positive. And the interesting thing is that they discover to do this combinatorics, you actually don't need to write down the wiring diagram. You can just write down a directed graph, of course, whose vertices are the chambers and which records which chambers are connected to each other. And then they discovered you can do these exchange relations which don't come from braid moves. And these will give you functions which are not minors, but are still positive on the space of totally positive matrices here. And they called these cluster variables. Okay, and this they generalized to an abstract cluster algebra. And interestingly, one of their initial motivations was to use cluster algebras to generate all the positive functions on spaces like these, which come from Lusztig's canonical basis. This is called the dual canonical basis, and that's still an open problem. So I think it's known that you can get a subset of the dual canonical basis this way, but not everything.
So here you're only considering topmost minors.
Yes.
So how do you know that like the non-topmost minors are positive?
Okay. Okay, good question. Okay, maybe I should have defined this, that only topmost minors are positive. Yeah, I think you're right. It actually is equivalent, but yeah, for this illustration, let's just say only topmost.
What's the rule of labeling the chambers again?
Sorry?
And catch what's the rule of labeling chambers?
So it's the wires which pass below the chamber. Like this labels 2 because 2 is the wire passing below it. Yeah. Okay. So I want to talk about total non-negativity for flag varieties. So a flag variety is just a G mod P, where P is a parabolic subgroup. And here we should take it to be compatible with our pinning. So it should be generated like by B and some YIs. And then the totally positive part of G mod P, sorry, is just the image of the totally positive part of G modulo P. And the non-negative part is the Euclidean closure of that, which generally strictly contains the image of the totally non-negative part of G, which is one thing that makes this kind of a lot more subtle to study. And this is something that, I mean, people could have studied in the 50s for, you know, Grassmannians or complete flag varieties, but somehow it didn't come up until Lusztig's work. So kind of a fundamental and still very interesting example is the case of a Grassmannian, GR K comma N, which is just the set of K-dimensional subspaces of Cn. For example, here's an element of GR24. So it's a 2-dimensional subspace of C4. And how I'm going to represent my elements is as 2x4 matrices, whose rows form a basis for V. And of course, there are many different matrix representatives. I could have chosen a different basis for V here, but I'm just going to mod out by that equivalence. And using these matrix representatives, we can define Plücker coordinates. So the Plücker coordinates here are the 2x2 minors of this matrix. So there are 6 of them. So example, if I look in the Plücker coordinate for columns 2 and 3, I take the minor in columns 2 and 3, which is 4. So that's why this is 4. Okay, and these are well defined. They don't depend on the choice of matrix representative up to global rescaling by a non-zero constant. So these are well-defined projective coordinates. And being totally positive just means all my Plücker coordinates are positive up to rescaling. So this is not obvious from the definition. What it's saying is that if all the Plücker coordinates are positive, then I can kind of find a matrix representative, which are the first 2 rows of a totally positive matrix. Which again is not obvious from Lusztig's definition, but it was proved by Reach in unpublished notes, and similarly for the totally non-negative part. And I just want to give maybe an assortment of, so this example here is totally positive. Okay, so I just want to give an assortment of interesting properties of these totally non-negative Grassmannians. So we have this result actually from 1950 by Gottmacher and Crane. So they were thinking about, matrices and their images, but we can phrase it in terms of the Grassmannian as follows. So if I have an element V of the real Grassmannian, so it's a subspace of Rn, then V is totally non-negative if and only if every vector in V has at most k-1 sign changes. And I just want to point out here, this k-1 is best possible. So if I take a matrix representative, which is row reduced, and then I take the alternating sum of the rows, that would give me k-1 sign changes. And similarly, V is totally positive if and only if every vector in the orthogonal complement, which is non-zero, has at least k sign changes. Okay. Another way to motivate this totally positive Grassmannian is actually the space of n by n totally positive matrices is in bijection with the totally positive part of the Grassmannian grm comma n plus n. So I have this 2 by 3 matrix here. I can embed it in the Grassmannian by putting an identity matrix here. And then I have my 2 by 3 matrix on the right, except I've reversed the order of the rows and added some negative signs. And you can check that all the minors here, the collection of all minors here is precisely the collection of 2 by 2 minors. So for example, the entry B is the 2 by 2 minor in columns 1 and 4. And so this identifies the space of totally positive matrices with this totally positive part of this Grassmannian. But the totally non-negative parts are different, because the totally non-negative part of the Grassmannian is compact. So we can view it as kind of a natural compactification of the space of totally positive matrices. So if we want to understand the boundary structure of the space of totally positive matrices, it makes sense to work in the Grassmannian. By the way, another interesting thing is that this Grassmannian has a cyclic symmetry. So I can kind of rotate, I can move this first column to the end and negate it, and that will preserve total positivity. And that action is kind of obscured on the level of matrices. And for example, there's work of Farber and Postnikov where they study maximum and minimum collections of minors for totally positive matrices, and it was important that they kind of move the problem into the Grassmannian. Okay, I also want to mention this curious result of my collaborator Kevin Purbhoo, which says that if we have a totally non-negative element of the Grassmannian, it's a generating function. So the sum over all subsets I of the Plücker coordinate delta sub I times the product over all variables x sub I for little I in my subset is a stable polynomial. So it's non-zero when all these xi's live in the upper half plane of the complex plane.
That's not if and only.
Well, yeah, so if these coefficients satisfy the Plücker relations, then it's yes, if and only if. But that's a consequence of, so if you have a homogeneous multi-affine stable polynomial, all its up to rescaling, all its coefficients are positive. It's the phase theorem of Coe, Oxley, Sokal, and Wagner. Okay, some other results about this space. It has a beautiful cell decomposition. So a cell decomposition of a space is just a way to partition it into pieces, each of which is parametrized by a product of the positive real numbers. So it's homeomorphic to an open ball. And Postnikov found an explicit description to what are called positoroid cells. For each polar coordinate delta sub I decide whether it should be 0 or positive. And those constraints, maybe they can't be satisfied. It's like some positive matroid realization problem, but if they can be satisfied, then we get a cell. And each cell is parametrized by a Playbit graph. So a Playbit graph is a planar bicolored graph like this one, and I won't explain how, but there's some recipe to turn this into an element of the Grassmannian. So this, every Grassmannian has a unique top dimensional cell, which is the totally positive part. And here it is for GR24. Another way to think about this totally non-negative Grassmannian is more geometric. And it goes by looking at the case when k equals 1. So when k equals 1, GR1 comma n is a projective space. For example, GR1 comma 3 is projective space P2. And its non-negative part is a simplex. Here it's a triangle. And to see that, just note that like the interior is where all the Pluger coordinates are positive, and then we get to the boundaries by sending some Pluger coordinates to 0. And when k is not 1, the boundary structure is complicated because there are Pluger relations. So there are relations between these Pluger coordinates, which mean if I send some Pluger coordinates to 0, I may have to send other Pluger coordinates to 0. But when k equals 1, we have no Pluger relations, so we just get a simplex. So how you can think about the totally non-negative Grassmannian is it's the Grassmannian analog of a simplex. And then you could ask, as Lamb did, what's the Grassmannian analog of a convex polytope? So he defined that. It was actually introduced by physicists in a special case called the amplituhedron. And it's related to scattering amplitudes. And this has led to the theory of what are called positive geometries, which was an important new development in physics. And there was a conference earlier this year I hear about this subject. Okay. I also want to briefly mention other partial flag varieties in C to the n. So an arbitrary partial flag variety in C to the n is just determined by a choice of ranks, K1 through Kr. And then I'm considering partial flags where I have subspaces of dimensions K1 through Kr, and they have to be mutually nested in each other. Okay, so V sub Ki is dimension Ki for all I. And so if I just have one Ki, then I get the Grassmannian back. If I have all the ranks 1 through n minus 1, I get what's called the complete flag variety. And this complete flag variety has a very nice boundary structure. So here I'm depicting it when n equals 3. And it's actually 3-dimensional, which is nice for visualizing it. So on the right here, we kind of have a combinatorial abstraction of it. So these vertices here are the elements of the symmetric group S3. So they're permutations of the numbers 1, 2, 3. So there are 3 factorial of them. And the edges here are the edges in the Hasse diagram of the strong Bruhat order. So the strong Bruhat order is a partial order on Sn where we move up in the partial order by taking two numbers which are in order and swapping them. So for example, here, if I take 1 and 3, which are in order and swap them, I get 3, 2, 1, which is bigger in this Bruhat order. So the edges are the cover relations, so the minimal relations. And then we have 4 2-dimensional faces, which are the 4 intervals of rank 2. And then we have 1 3-dimensional face, which is the interval from the top to the bottom. And on the left here, from a couple different angles, I've plotted this space in kind of more real coordinates. And you can see it is a space with 6 vertices and 8 edges and 4 2-dimensional faces.
Are you saying the permutation flags are totally not negative?
Yes. Yes, so they're not represented by totally non-negative matrices, but they are limits, mod B of totally positive matrices.
Okay.
Yeah, so for example, like if I took this matrix mod B and I took T to infinity. Sorry, I'm on here. I would get this permutation. Okay, so I'm just a result I proved recent with Tony Block, which came up in our work on dynamics, is that actually this, for even in these type A partial flag varieties, the Lusztig total positivity can differ from positivity of Kluger coordinates. So if a partial flag is Lusztig totally non-negative, then all the Kluger coordinates are non-negative of all the VKIs. But the converse does not necessarily hold. In general, there can exist partial flags which are Kluger non-negative but are not Lusztig non-negative. And the two notions are the same if and only if these ranks are consecutive. And this is actually interesting, for example, in physics, because in the physics connection, this n there's like n particles, and there's a natural cyclic order on the particles. So there should be some cyclic symmetry here. And it turns out that this Kluger non-negativity has a cyclic symmetry if all the ranks have the same parity. So if the ranks are all odd or all even. But in general, this Lusztig non-negative part does not have this cyclic symmetry. So, for example, in studying spaces called loop amplituhedra, it's more natural to use this Kluger positivity. Okay, the last part of this intro, I wanted to justify total positivity from this perspective of topological combinatorics. This goes back to work of Björner about 50 years ago. And it has to do with regular CW complexes. So a CW complex is some sort of cell complex, and regular is an additional property. But how you can think about it essentially is that it's a cell decomposition. So a partition of a space into open balls, such that the closure of every cell is homeomorphic to a closed ball. And in combinatorics, the prototypical example of this is a polytope, where the cells are the open faces, and the cell closures are closed faces, which are closed balls. Here's an example of a regular CW complex, which is not a polytope. So it has these two vertices and two edges, and this interior, and every closure is homeomorphic to a closed ball. And this is something that's not regular, because, for example, here we have this one-dimensional face, which is an open line segment, and its closure is this circle, which is not the one-dimensional closed ball. Okay, it's actually not even contractible. So why should we care about these? So Björner showed that CW complexes are combinatorial objects. So they're uniquely determined up to homeomorphism by the closure poset. So this is the poset which tells us when one cell is in the closure of another. And basically why that is the poset just tells you recursively how to build up your regular CW complex by gluing closed balls, and then how to do the gluing onto your existing skeleton. And conversely, there are natural combinatorial conditions which imply that a given poset is the closure poset of some regular CW complex. That's called being graded, thin, and shellable. Okay, so graded and thin are kind of the trivial properties, and shellable is an interesting combinatorial one, and there are lots of techniques people have developed for proving shellability. And there are interesting posets which are graded, thin, and shellable, but they don't come from polytopes. So one example is shown by Edelman, is the symmetric group Sn. So this is the one we saw before. So this is S3 and the Purbhoo order. And now how I'm thinking about it is it's supposed to come from a two-dimensional regular CW complex. So So in this picture, this bottom element is the empty set, so I ignore it. And then these two things are two vertices, and these two things are two edges, and this is a two-dimensional face. So actually, this is the closure coset of this regular CW complex here, which cannot come from a polytope. So if we want to geometrically realize spaces like these, we need to move beyond the world of polytopes. And Björner posed the question, well, we can build a regular CW complex with this closure coset just by this recursive gluing procedure, but is there like a naturally occurring space in mathematics with this, which is a regular CW complex with this coset? And at the time, people didn't know how to answer Björner's question, and that was because this was before Lusztig's work on total positivity. And what they showed was that actually this link of the identity in this totally non-negative space UN we saw before is the correct regular CW complex. So this was something they conjectured actually for any file group, and it was proved by Hirsch. So I just show what it is in this example. So here I'm looking at this space we saw before, but now I'm looking at the totally non-negative part. So all minors are greater than or equal to 0. And this space is closed, but it's not compact. So to compactify it, I'm going to take the length of the identity, which just means the sum of the entries immediately above the diagonal are 1. And then I get a two-dimensional space, and I can just plot it in the plane, like the AB plane. And what you get is a thing bounded by a line and a parabola. So you indeed get this two-dimensional regular CW complex from the previous slide. Okay, and so I just want to mention some other examples of regular CW complexes. So I mentioned polytopes are one example, and actually the totally non-negative part of a toric variety is also a regular CW complex. And this is explained by Sottile, where the algebraic moment map gives a homeomorphism to its moment polytope. Also objects called toric cubes, introduced by Engstrom, Hirsch, and Sturmfels, and proved by Basu, Gabrielov, and Vorobyov that they're regular. The totally non-negative part of a partial flag variety. This was conjectured by Postnikov and Williams, and it was proved in joint work with Goloshin and Lamb for reductive groups G, so in finite type, and then it was generalized to the Katz-Moody case by Bao and He. And there's recent work of He, Simpson, and G on totally non-negative matrix Schubert varieties, which shows the regular CW complexes. But this is kind of expected to hold much more broadly. So for these Grassmannian generalizations of polytopes, including amplituhedra, it should also work for the totally non-negative part of a cluster algebra with a nice cluster variety structure, and also maybe spaces of Lorentzian polynomials. And yeah, so I would say at this point, our techniques for doing this are either kind of specific to the toric case or specific to the algebraic group case, and really using the multiplication structure on an algebraic group. So it would be nice to have some more general techniques that apply to these other settings. All right, thanks. So this is the end of the first part, and then if you want to stick around for the second part, I'll talk about Schubert calculus.
Questions?
Yeah.
Let's say if you look at Lorentzian matrix, do we have an analog for test? Like how many what is subset of minors you have to check for signs to show that matrix exists?
That's a good question. I don't know that I or anyone else has thought about that. Yeah.
So what does or is there a quick way to describe what the CW cell decomposition looks like for a G mod P for the totally non-negative part?
Yeah, so the cell decomposition is so for G mod B, we just get intervals in Brouwer order. And for G mod P, we get intervals in Bruhat order where the upper element is a minimal length coset representative of the Weyl group modulo the parabolic subgroup corresponding to P.
Is that related to matrix stratification?
Yeah, I guess that's.
Yeah, I mean, so if you kind of intersect the matroid stratification with the totally non-negative Grassmannian, you get the positroid stratification. But yeah, I mean, of course, like there are these, Mignov universality theorems about how the matroid stratification is bad. And these stratifications are like as nice as possible. So this is not really seeing any of the bad behavior.
Yeah, so the cells are positroid realization spaces.
Yes. Well, like such that all the Kluger coordinates are positive.
Yeah.
They're positively oriented matroid realization space. Yeah. Danny.
Some of these, or maybe all of them, I'm not sure, are also maybe expressible as semi-algebraic sets. Is there any interaction between the topological combinatorics and the algebraic structure?
Yeah, that's a good question. I mean, certainly, like one way to think about it is if you have a semi-algebraic set, this gives a natural way to try to decompose it into cells. That for each function, you either say it's positive or zero. So then there's a question of what like kinds of semi-algebraic sets, for example. So if you have a cluster algebra and you set all the cluster variables greater than equal to zero, that's a semi-algebraic condition. But does this give you a regular CW complex always? Or can you do it more generally, or does it have to be less general?
Can you express like a general conjecture which contains all those conjectures?
No, that would be really nice, but it's hard to connect these various settings. I mean, another case that might be related is like, there's the Thurston compactification of type Müller space, which is a homeomorphic to a closed ball. But we don't know if that's related.
Like the measured laminations that.
Maybe. Yeah, probably.
Okay, maybe 10-minute break.
Okay.
We should start. Let's start. Steven will continue.
Okay.
It's like a part.
Thanks. Okay, so this is joint work. A couple of papers, one joint with Kevin Purbhoo and the other with Evgeny Mukhin and Vitaly-Tarasov. So just to set the stage for what kind of Schubert calculus we're doing here. So we're working over we're solving a Schubert problem in this Grassmannian. Here I've changed notation. This is to match my paper with Kevin. So we have a Grassmannian of d-dimensional subspaces of Cn. And I'm fixing several Wi's in this Grassmannian, so subspaces of codimension D. And the condition is that V intersect each of these Wi's non-trivial. So generically, if V is dimension D and Wi is codimension D, then they'll intersect in just the origin. So I want that not to happen. And D times M minus D, this is the dimension of this Grassmannian. And each of these conditions is codimension 1. So it's plausible that this problem has a finite number of solutions. And it turns out it does. And by the way, I call this a divisor Schubert problem because each of these conditions is saying V lies in some Schubert divisor. And in this talk, I'm not going to consider more general Schubert conditions, which are higher codimension, and I'm not going to consider problems on other varieties. just the Grassmannian. Okay, so here's the standard example when D is 2 and M is 4. We're looking at two-dimensional subspaces of C4, but if we projectivize, they become lines in three-dimensional projective space, and D times M minus D is 4. So I have 4 lines W sub I, and I want to find all lines V intersecting all 4. And if the WIs are generic, there are 2 solution lines. And even in this simple case, it's hard to visualize the 2 solution lines in general, but if the WIs are in some sort of special position, we can visualize them. For example, if W1 and W2 intersect and W3 and W4 intersect, there are still 2 solution lines and we can visualize them. So does anyone want to do the honors of pointing out at least one of the solution lines? Okay. I saw someone make a hand gesture, which, so this line is one of them through the 2 intersection points. What about the other line?
Where the planes intersect.
Okay, thank you. So each pair of lines spans a plane, and the planes, generically 2 planes in a 3-dimensional space will intersect. That's the other solution line. Okay, and in general, when these WIs are generic, the number of solutions is the number of standard Young tableau of rectangular shape D by M minus D. So in this case, these 2 solutions are in bijection with these 2 standard Young tableaus. So that means I have this 2 by 2 square, and I fill it with the numbers 1, 2, 3, 4, such that it's increasing along rows from left to right and increasing down columns from top to bottom. Just as an aside, one of the motivations of my collaborator, Kevin Purbhoo, is to, like in general, I don't think there's a canonical bijection between solutions and these tableaus. But kind of using the real stuff I'm going to talk about, there's a way to do this bijection and then to do tableau combinatorics using Schubert calculus. So he has some nice papers on that. Okay, so now what we want to do is so this was all over the complex numbers, and working over the complex numbers is nice because it's algebraically closed. But in applications, if we have a system over the real numbers, we want to solve it over the real numbers. And so Fulton in the 80s posed this question: if we have an enumerative problem, how many solutions can be real? So for example, do there exist Schubert problems where all the solutions are real? And in the 90s, the Shapiro brothers, Boris and Misha, came up with a beautiful conjectural answer. They were actually motivated by total positivity, but in any case, this gives an answer to Fulton's question. So what we're going to do is consider this special curve called the moment curve gamma of t, which just consists of all the powers of t from m minus 1, m minus 2 down to 1. And I rescaled by these factorials, just because that's going to be relevant later. But really, for this statement, for now, you can take any actually rational and normal curve, gamma. And I'm going to let each wi be an osculating subspace. So how I get an osculating subspace is I just choose a real point t, and then the wi is spanned by gamma of t, the first derivative of gamma at t, and the second derivative of gamma at t, and so on until I get m minus d points to span an m minus d dimensional subspace. And then the conjecture is that, first of all, the behavior is generic. So we have the expected number of solutions and that all the solutions are real. So here's the same example from before for GR24, again, projectivized. And this is a paper from a nice survey paper of Frank Sottile. And here this gamma is a curve called a twisted cubic. And here the oscillating subspaces are just tangent lines. So I choose 4 tangent lines to this curve. So these are the magenta line here, this red line here, the green line here, and the brown line. And then we want to find all black lines which intersect the 4 given lines. So they're a bit hard to see, but one solution line is here. And then the other solution line is this one here. And then this is an arrow pointing this solution line. And this yellow thing is a hyperboloid, which turns out to contain both solution lines. Okay, so the conjecture is saying, no matter how you pick these tangent lines, the 2 solution lines will be real. rather than being non-real complex conjugate. And this holds for a general Grassmannian. Okay, so just a couple of comments. So first of all, this is not just like a kind of cooked up Schubert problem. It actually comes up naturally in a couple of places. So one, it came up in work of Eisenbud and Harris on linear series on algebraic curves. It comes up in the theory of ODEs. That'll be implicit a bit later. It's also applicable to pole placement problems in control theory, as Tony and I were discussing this week. And the other point I want to make is that there's actually a very rare property to have all real solutions. So inspired by Sottile's work on this, Bergerser and Larario initiated the study of probabilistic Schubert calculus. So this Grassmannian is a compact manifold. So it has a Hart measure, and we can let these WIs be uniformly random elements of this Grassmannian. And then we could ask, if they're uniformly random, what is the expected number of real solutions, V? And they show that the expected number of real solutions is approximately the square root of the number of complex solutions. So for large problems, basically 0% of the solutions are real.
This for like any Schubert problem or this particular Schubert problem they showed it for?
For any Schubert problem where these WIs are uniformly random in the Grassmannian. Yeah.
No, wait, what? For like, it doesn't matter if you do a different.
Sorry?
I don't believe you.
So, okay, so the statement is
Is it, I think Bill's question is it just the intersection of divisors or is it just every possible? Is it?
yeah, just the intersection of divisors.
Okay.
Yeah, I mean, I think if these are uniformly random, it kind of, yeah, you would not get special.
Okay.
Yeah. So, yeah, sorry, yeah, that's just for this divisor Schubert problem. Okay.
But I mean, I was all interested in other, you don't think it's true for like other kinds of Schubert problems? Like ones where you have, on the flying right.
Sorry, this result?
Yeah, like their result is, they just proved it for this.
Yeah, it's just for the Grassmannian divisor Schubert problems. Yeah, it could be interesting in other cases what happens. Okay, so a bit of history about this conjecture. So as I understand it, it was formulated privately by the Shapiro brothers in the early 90s, and then they told it to Frank Sottile at a conference in 1995, and Frank Sottile got very excited about it. He kind of advertised the conjecture. He tested it extensively with computer. Actually, the original conjecture was way too general, so he kind of found some counterexamples to the original conjecture and refined it to the statement on the previous slide, and he proved it asymptotically. So he proved it if the oscillation points are sufficiently far apart. Eremenko and Gavrielov proved the case of dimension or codimension at most 2. And this is interesting because it's a statement about rational functions, it turns out. It says any rational function whose critical points are all real is itself real up to equivalence. And Mukhin-Tarasov and Varchenka gave a proof of the full conjecture using a completely different technique. So it involves a deep connection with representation theory called the beta ansatz. And I'll probably say a bit more about that proof later, but this proof was kind of studied and simplified by my collaborator, Kevin Purbhoo, and that was one thing that led to our joint work. Levinson and Purbhoo gave a completely different topological proof of the conjecture. So the idea of this is that if we know the conjecture is true asymptotically, and then what we do is we kind of move our WIs, our oscillation points around. And as we do that, it just suffices to show that all the solutions remain distinct. Because if all the solutions are real and they're moving around, the only way solutions to become non-real is if two solutions collide and then become complex conjugate non-real pairs. So that's what they work at.
What does asymptotically mean here?
So my WIs were like oscillating subspaces. The points, so it just means the points of oscillation are spaced sufficiently far apart. Okay, and just to mention, so I kind of motivated this by Fulton's question about whether there exist Schubert problems with all real solutions, and Vakil using different techniques. So this was his work on Schubert induction, part of his work on the geometric Littlewood-Richardson rule. And he showed that any Schubert problem on a Grassmannian, for not just divisor Schubert problems, but arbitrary Schubert problems, there exist instances where all the solutions are real. And so this actually results, you can take limits and get a different proof of the Kiel's result. Okay. So what I want to talk about now is a generalization of the Shapiro conjecture due to Sottile called the secant conjecture. And I call it the divisor form because, again, it's only for these divisor Schubert problems. And there's a more general version for more general Schubert problems. And I've kind of highlighted the parts that are different. So we're still considering this special moment curve gamma. And before these WIs were oscillating subspaces. Now they're going to be secant subspaces. So a secant subspace means I just take m minus d points along my curve and take the subspace spanned by those points. And if the points I choose for different subspaces don't overlap with each other, then we still get all real solutions. And the Shapiro conjecture is a limiting case of this one, because if I take my points of secant C and let them collide, then the secant subspace limits to the oscillating subspace. Okay, and Eremenko, Gabrielov, Shapiro, and Weinstein, they prove the case when V has codimension at most 2. And what I want to present now is our proof of this secant conjecture for divisor Schubert problems. Okay, so to do that, I first kind of want to reformulate some stuff I've discussed in terms of an object called the Wronski map. So what the Wronski map does is it takes some d functions, say from C to C, and it spits out a function also from C to C, which is the d by d determinant of the functions and their derivatives up to order d minus 1. If you haven't seen this before, I want to try to motivate why it's an interesting object. So for example, the Wronskian of 2 functions f and g is this 2 by 2 determinant. And you get this thing which looks like the denominator in the quotient rule in calculus. Actually, it's f squared times the derivative of g over f. So the zeros of this Wronskian are telling you what the critical points of this rational function. Okay, another nice thing is the Wronskian tests for linear independence. So my functions f1 through fd are linearly independent if and only if the Wronskian is not identically 0. And in this case, the Wronskian is a well-defined function of the span of my function. So in other words, if I let V be this d-dimensional space of functions spanned by my f1 through fd, then this Wronskian, if I do a change of basis and choose a different basis for the same subspace V, this will not change the Wronskian up to just rescaling. So in particular, the zeros of this thing are well-defined in terms of V. And the zeros have a nice interpretation. They're points in the complex plane where some non-zero function f in V has a 0 of unexpectedly high order greater than or equal to d. So the idea here is that by linear algebra, so think like Lagrange interpolation, if I choose any point in the complex plane, there is going to be a non-zero function which has a 0 of order d minus 1 at that point. But for some special points, the 0 of order d minus 1 might have higher order. And so those are the zeros of the Wronskian. Okay, a final thing, the Wronskian comes up a lot in differential equations. So if you taught a course on differential equations, you've probably seen this Wronskian. And one way to explain that is as follows. So V here is a d-dimensional space of functions. So it should be the solution space of a linear ODE of order d. And we can write down this ODE explicitly using the Wronskian. So the ODE is just the ODE which is the kernel of L. And L is this differential operator, which takes the function g to the Wronskian of f1 through fd and g divided by the Wronskian of f1 through fd. And why is that? Well, this is 0 if and only if this numerator is 0, which means these functions are linearly dependent, which means that G should be in the span of F1 through Fd. Okay, and then the reason I'm dividing by this Wronskian here is just to make the operator monic. So the coefficient of the dth order derivative is 1. And for example, this also gives another meaning to the zeros of the Wronskian. They're the points where this differential operator is singular. Okay, so now I want to connect this to what these Schubert calculus I was talking about. So we're going to identify our vector space C to the m with a vector space of polynomials of degree at most m minus 1, which I'm denoting like this. And how that identification works is it just sends a vector a1 through am to the polynomial whose coefficients are a1 through am, where I've rescaled like u to the j by j factorial in the denominator. Okay, and then I'm going to think about elements of this Grassmannian as d-dimensional spaces of polynomials of degree at most m minus 1. And so given a subspace here, I take its Wronskian, which is well defined up to rescaling. That's why I have this projective P here. And generically, well, okay, so the Wronskian of several polynomials is itself a polynomial. And it's going to have degree at most d times m minus d. And generically, it will have degree exactly d times m minus d. So algebro-geometrically, this is a nice finite flat morphism. Its degree is the number of standard Young-Tableau of rectangular shape. Okay, the connection to what I was talking about before is the following. So we were looking at Schubert problems defined by osculating subspaces. So V was supposed to non-trivially intersect some osculating subspaces. And this lemma says that V non-trivially intersects the oscillating subspace to our moment curve at Z, if and only if the Wronskian of V has a 0 at negative Z. So in other words, if specifying the zeros of the Wronskian and then solving for V is equivalent to solving the Schubert problem for oscillating subspaces. Or if we want to restate this Shapiro conjecture, it says that if I have a point of the complex Grassmannian and all complex zeros of the Wronskian are real, then V itself is real. So it has a basis of real polynomials. Okay. So here's just an example again for GR24. And let's suppose this is my Wronskian. So generically for GR24, Wronskians are supposed to have degree 4. So you can think here that there are 2 more zeros at infinity. And it turns out there are 2 solutions, V with this Wronskian, this space of polynomials and this space of polynomials. And the conjecture, which was proved by Mukhin-Tarasov and Varchika, says that if Z1 and Z2 are real, then these spaces of polynomials are real. Okay, so Z1 and Z2 are real. Actually, these are all real polynomials. And this happens generally. Okay. So now what I'm going to talk about is a couple of more conjectures, which are increasingly stronger. So first one is a conjecture of Eremenko from 10 years ago, which we call the disconjugacy conjecture. And it says that if I have an element of the real Grassmannian, which again, I'm thinking of a d-dimensional subspace of real polynomials, and all the complex zeros of the Wronskian are real, and I'm going to let K be any real interval which avoids these zeros. Then the conclusion is that every non-zero real polynomial in my vector space has at most d minus 1 zeros on that interval. So again, the idea here is that by linear algebra, this interpolation idea, if I choose d minus 1 points in K, there will exist some F with zeros at those points, but I can't have any more zeros in K than those d minus 1. And Eremenko showed that this implies actually the divisor form of the secant conjecture. And I won't go into details, but this follows from like some souped up version of the intermediate value theorem called the Poincaré-Miranda theorem. And the idea is that in the divisor secant Schubert problem, we're considering our WIs are like secant subspaces. And what this conjecture implies is that, you know, in the Schubert problem, we have this condition that V intersects this secant subspace. And actually what we get from this conjecture is that V is going to intersect an osculating subspace where the point of oscillation is a point in this interval. And so if we do this for each of the secant subspaces, we get that each solution V to the secant problem is a solution to the osculating Schubert problem. And therefore it's real by the Shapiro conjecture. So if you didn't follow that, just think of this as some intermediate value theorem argument. Okay, another conjecture is a positive version of the Shapiro conjecture. So again, I've highlighted the parts which are different from the Shapiro conjecture. It says that if all the complex zeros of the Wronskian of V are real and non-positive, then V is not only real, which would be the Shapiro conjecture, but V is also totally non-negative. So all its Pucher coordinates are non-negative. So, okay, so you might wonder, like, why consider this statement? So maybe, you know, maybe it's an elegant statement, but why I was interested in it is because I was able to show its equivalent to Eremenko's disconjugacy conjecture. And kind of one direction is easy, so it's kind of easier to prove the positivity conjecture implies the disconjugacy conjecture. And the interesting part was kind of proving the converse, which actually involves a new characterization of the totally non-negative complete flag variety. But as it turns out, what Kevin and I proved is we actually proved this positivity conjecture. So we only need this kind of easier implication. And I just want to briefly explain that proof because it uses some stuff from the first part of my talk. So what I want to do is assume the positivity conjecture is true and prove this disconjugacy conjecture. So it turns out that in all this stuff, there's an action of SL2R, which, you know, commutes with everything, or is compatible with everything. And using this action of SL2, I can turn my interval K into the positive real line from 0 to infinity. So what that's saying is that here I'm assuming all the zeros of the Wronskian are real and the positive real line has no zeros. So in other words, all the zeros of the Wronskian are real and non-positive. And then the positivity conjecture tells me that in that case, V is totally non-negative. And there was this classical result of Gontmacher and Crane that if V is totally non-negative, each vector viewed as a sequence of numbers changes sign at most d-1 times. And so that means if I'm thinking of my vector space as a space of polynomials, its sequence of coefficients has at most d-1 sign changes. And then Descartes' rule of sign tells me that if I have at most d-1 sign changes, I have at most d-1 positive zeros, which is the conclusion we needed for the disconjugacy conjecture. So this implication is actually uses these classical results. Okay, so to summarize where we are, we had all these conjectures and they kind of all follow from this positivity conjecture. So
is the positivity conjecture saying something about the inverse image of the positive part of the projective space under the Wronski map?
yeah, I guess it's saying it's contained in the totally non-negative Grassmannian. Yeah. By the way, this implication is quite weak. So if you think just for d equals 1, the Wronskian is just a single polynomial. So for d equals 1, this is saying if a polynomial of a single variable, all its complex zeros are real and non-positive, then the coefficients are non-negative up to rescaling, which is quite a weak statement. So yeah, so one thing I'm interested in is like how can you somehow strengthen this result? But this, I mean, this result was already, you know, quite powerful enough to prove these different things. Okay, so our proof, how our proof goes is what we do is solve what we call try to solve the inverse Wronski problem. So kind of computing the Wronski map in the forward direction is not too bad. So if I'm given a subspace V, how do I calculate the Wronskian? Well, I just choose a basis of V and then form the d by d determinant and take the determinant. But now what I do is want to solve the opposite problem. I want to know if I'm given the Wronskian, and even say, let's say I know what its zeros are, it's completely factored over C. How do I solve what V is? And of course, there are going to be many different solutions V. And now in general, we shouldn't expect to do this because this is solving some Schubert problem. And in general, if we're given some system of polynomial equations, we don't expect to be able to solve it exactly. But what we do is we do solve this inverse Wronski problem exactly over the group algebra of the symmetric group. And this turns out to be sufficient to prove this conjecture. So that's what I want to explain. So the conference earlier this semester, Lauren Williams said that if you are working with Plucker coordinates, you should always try to think of them as being indexed by partitions. And that's what we want to do here. So partition lambda is a weakly decreasing sequence of non-negative integers. The size of lambda is just the sum of these numbers, which is 5 in this example. And we're going to think about partitions whose diagram. So the diagram is just boxes where the row lengths are the entries here. So I have rows of length 2, 2, and 1. And I want partitions fitting inside a rectangle where this side is D and this side is M minus D. For example, if D is 3 and M is 7, I'm looking at a 3 by 4 rectangle. And then what I do is trace this border from the bottom left to the top right, and I write down the numbers 1, 2, 3 up to M. And then I take the labels of the vertical steps, which here are 2, 4, and 5. And this forms a D-element subset of the integers 1 through M. And this is a one-to-one correspondence. Okay, so the point is just, I just want to index my Plucker coordinates rather than by subsets. I want to index them by partitions, which is going to be very important for reasons we'll see shortly. Okay, so here's our main theorem. So we're going to fix some complex numbers, z1 through zn. These are the negative roots of the Wronskian. Then there exist linear operators beta lambda, which are functions of the z's, such that these three properties hold. So the first property is that these linear operators pairwise commute, and they satisfy the Plucker relations. So the Plucker relations are quadratic relations which cut out the Grassmannian as a projective variety. And using this correspondence, we can translate the Plucker relations and express them in terms of partitions. So these beta lambdas satisfy these Plucker relations. Part 2 says, well, these operators pairwise commute. So we can decompose our space into common eigenspaces. And if I take a common eigenspace E of these beta lambdas, then each beta lambda just acts as a scalar multiple of the identity. So it acts by its eigenvalue. And if I look at the collection of eigenvalues, I get a collection of complex numbers indexed by partitions, which satisfy the Plucker relations. So they're the Plucker coordinates of some point of the Grassmannian, and this point V of the Grassmannian has the Wronskian U plus C1 times U plus C2 up to U plus Cn. So it has the desired Wronskian. And this is a one-to-one correspondence between Grassmannian elements V with this Wronskian and common eigenspaces of these beta lambdas. Okay. The third part is how we get the positivity conjecture. So the positivity conjecture was that if the zi's are non-negative, then these Plucker coordinates are non-negative, which is equivalent to saying these eigenvalues are non-negative. And what we show is that the beta lambdas are positive semi-definite operators and hence have non-negative eigenvalues.
On which space are these defined?
Good question. So yeah, I kind of delayed the definition, which is the most important part of the theorem. how are these beta lambdas defined? So these beta lambdas live in the group algebra of the symmetric group. So this is just the space of formal linear combinations of elements of this symmetric group Sn. And how it's defined is I sum over all subsets of the integers 1 through n, whose size is the size of lambda. So if the size of lambda is bigger than n, it's just 0. And here I have a product of all the zi for I not in my subset. And then here I have a sum over all permutations pi, which are only allowed to permute the elements of x. And here I have the permutation pi. And out front, I have this number, which is the irreducible character evaluated at pi. So this is using the fact that the Plural coordinates are indexed by partitions, but partitions also index irreducible characters.
What was the motivation for defining this operator?
Yeah, excellent question. So in Kevin's, in kind of Mukhin-Tarasov's and Varchinka's work on this, these operators naturally arose when lambda is a single column. And then in Kevin, my collaborator Kevin Purbhoo's previous work, he kind of had these dual operators where lambda is a single row. And then he wondered, what if you just plug any irreducible character in here? And then he thought, well, then there's indexed by partitions, which hopefully index plural coordinates. Wouldn't it be miraculous if these actually gave the plural coordinates? And so he did extensive tests on Sage, and it seemed to work out. So yeah, even now we don't have kind of an a priori justification for why to consider these operators. So that would be something interesting to know. And also, can you generalize them to other groups?
What's the relation between n and d?
So n is just the number of zeros of the Wronskian.
And is that related to the Grassmannian?
So n has to be at most d times m minus d. So what is going on is n is actually the size of the Schubert cell, the size of the partition indexing the Schubert cell in which V lives. And Zhaoji, to go back to your question, this correspondence is actually respects Schubert cells. So what you do is these are elements of the group algebra, the symmetric group, but you view them as acting on an irreducible representation, say indexed by the partition nu. And then if your eigenspace is contained in that irreducible representation, the solution V will be contained in the Schubert cell indexed by nu. Okay, to be concrete, let's see some examples. Actually, I did want to make some comments here. So one comment is actually parts 1 and 2 of the theorem are actually completely general. They hold for any zero-dimensional algebraic variety. And what you do is you just let beta lambda be multiplication by the generators of the coordinate ring acting on the coordinate ring. And there's a result called Stickelberger's theorem, which tells you that then your points in your zero-dimensional algebraic variety are described by this correspondence. So what's kind of novel that we did was we found explicit formulas for these Stickelberger operators. In particular, in Stickelberger's theorem, there's no way to get like reality or positivity statements out of it. Another comment is, this idea of looking at linear operators and their eigenvalues is not even new to this problem. It was what Mukhin-Tarasov and Varchinka did to prove the original Shapiro conjecture. And what they did is instead of finding operators for plural coordinates, they found operators for finding the linear differential operator, whose kernel is V. And so, I guess how you can view our result is that, Mukhin-Tarasov and Varchinka found this differential operator, and then we solved this differential equation for the plural coordinates. Okay, so just to be concrete, let's consider this same example as before. D is 2 as M is 4, and let's take n equals 2. So my Wronskian has two zeros, negative Z1 and negative Z2. And in this case, my symmetric group is S2. It has two permutations, the identity and the transposition sigma. And so if lambda has size bigger than 2, then beta lambda is 0. So these are the only non-zero beta lambdas. And you'll just have to believe me that these are the formulas. And I guess the point is, like, for example, this is a minus sign here, because the irreducible character for this partition is the sign character. So the sign of the identity is 1, and the sign of the transposition is -1. Okay, and all these operators commute. That's not very interesting in this case because S2 is a commutative group. But for larger cases, it's a non-trivial statement. And we actually do have a non-trivial Pluker relation here. So this is the 3-term Pluker relation for the Grassmanni and GR24, written in terms of partitions. And remember that beta lambda is 0 if lambda has more than 3 boxes. So this term is 0, and this term is also 0. So the Pluker relation is saying this term is 0. And indeed, you can check like this thing times this thing is 0 in the group algebra. Okay. So what the theorem is saying is to look at a common eigenspace of these beta lambdas. It turns out there's 2 eigenspaces. One is the coming from the one-dimensional trivial representation. And then each permutation just acts as 1. So these are the eigenvalues of my operators. And I claim that these are the Pluker coordinates of this subspace. And the point is, if I write this subspace as polynomials, following my recipe from before, then this system of polynomials has the correct Wronskian, u plus e1 times u plus e2. And also, as I said, this is supposed to respect Schubert cells. So the fact I was working on this irreducible representation means I'm supposed to land in this Schubert cell. So this partition is supposed to be the largest partition of a non-zero Pluker coordinate. Okay, and then we can do the same thing for the other eigenspace for the sign representation. And then the identity acts as 1 and sigma acts as -1. So we get these eigenvalues, and these are the Pluker coordinates of this subspace, which is the other subspace with this Wronski. Okay. Just want to say a word about the proof. So one thing we had to show is these beta lambdas commute. And that turned out to follow from a trick from Kevin's previous work. And the other difficult thing we had to do was show that these beta lambdas satisfy the Pluker relations. It turns out once you do that, kind of everything else falls into place. And the way we did that was using a connection we've heard about a couple of times in the past few weeks, which is the connection with the KP hierarchy. So the KP equation is a PDE modeling shallow water waves like these waves here. And it's the first equation in a system called the KP hierarchy. And its solutions can be, in a certain system of variables, they can be expressed as symmetric functions tau in the variables x sub I, which satisfy some identity, which is called Heroda's identity. So what this identity is saying is here we have a symmetric function in the variables x, here we have tau in the variables y, and then I act by this linear operator here. And then here I'm acting by the adjoint of this linear operator here. And t is an auxiliary variable, and then I take the coefficient of t inverse, and this has to be equal to 0. So, if you're an expert in symmetric functions, I put the definition of what these operators are. And this perp thing is the adjoint. That's the conventional way to join adjoint with respect to the standard inner product, where the Schur polynomials are an orthonormal basis. And I guess the point is like so this KP hierarchy is supposed to be a system of PDEs, and how we get differential equations out of this is that the space of symmetric functions is freely generated by these PKs. These are called power sum symmetric functions, which are the sums of x1 to the k plus x2 to the k plus x3 to the k and so on. And the adjoint operator of multiplication by pk is k times differentiation with respect to pk. So that's how we get differential operators coming out of this. And what Sato showed is that this symmetric function tau satisfies this identity of Heroda if and only if its coefficients in the Schur basis satisfy the Pluker relations. And so if we want to know the beta lambda satisfy the Pluker relations, it's equivalent to show this sum satisfies the Hirota identity. So that's what we do. So this is a bit of like the reverse of how often people often view this connection, which is people often just take a point in the Grassmannian and then they get a solution to the KP hierarchy. And we're kind of doing the opposite. We want to get a point in the Grassmannian from establishing a solution to the KP hierarchy. Okay, and I also wanted to mention this because I think this is kind of an elegant formulation of the Plucker relations, which is probably not so well known. Okay, so in subsequent joint work with Evgeny Mukhin and Vitaly Tarasov, we gave a second proof, which uses more of this representation theory connection with the beta ansatz. So in particular, we're going to consider these operators, T lambda, indexed by partitions lambda, called higher Godin Hamiltonians. So these are going to act on this vector space, C to the D, tensored with itself n times. And H here is a D by D matrix. S lambda of H is the Schur polynomial and the eigenvalues of H. These Z1 through Zn, these are just complex numbers from before. And these bold Ds are matrix derivatives. So bold D sub I is the transpose of the usual matrix derivative, which acts on the ith tensor factor of this tensor product. Okay, so these were considered by Alexandrov, Laurent, Suboy, and Zabrodian, and they proved that these things pairwise commute and satisfy the Plucker relations. So the fact they commute is a consequence of the Yang-Baxter identity. And the fact they satisfy the Plucker relations, interestingly, they also used this KP hierarchy, Hirota's identity. Though it's not clear to me how our two proofs are related. Okay, so what we proved is that with Mukhin and Tarasov is that when this matrix is the zero matrix, then this T lambda becomes beta lambda. And remember, beta lambda was in the group algebra of the symmetric group, Sn, but Sn acts on this tensor factor, or this tensor product, by permuting the tensor factors. So beta lambda actually acts on here, and it's equal to T lambda at H equals 0. And then we have this positive semi-definite statement. So if the Zi's are non-negative and H has non-negative eigenvalues, then T lambda is positive semi-definite. And part 2 actually gives us a more general positivity theorem for spaces spanned not just by polynomials, but spaces defined by what my collaborators call quasi-exponentials. So these are functions which are an exponential function times a polynomial. And this is actually just also a limiting case of the polynomial case, because, like, you know, exponentials we can write as limits of polynomials. Like e to the u is 1 plus u over n to the n as n goes to infinity. Okay. And then, okay, maybe in the interest of time. So here I have some explanation of how you actually calculate these matrix derivatives. So if you're very interested in that, I can show you later, or you can look at my slides online. But I guess one reason I was interested in like showing this is because I don't think people have really studied these kinds of matrix derivatives, like combinatorialists, sorry, have studied these kind of things, but it could be interesting to study, you know, derivatives where you replace S lambda with some other symmetric function, like a Macdonald polynomial. Okay, so here are some things, some further work. So I think it would be interesting to explore the connection with the KP hierarchy. Like, do these Wronski solutions mean anything for the PDEs? It would be nice to generalize this Eisen-Schoenberg-Whitney theorem. So this characterized real-rooted polynomials in terms of, or polynomials with non-positive real roots in terms of the coefficients. And we'd like to do the same for the zeros of the Wronski and in terms of the Plucker coordinates. And also there's lots of generalizations of this conjecture. Of the Shapiro conjecture and the secant conjecture that I'm interested in. All right, thank you. Yeah, David.
Can you go back to slide 6? Why, where does this how do you think about this identification?
This one?
Yeah. What makes that natural? It reminds me of Connor's talk. When he considered the action of Cn on. Yeah, sorry. There's that. Maybe
Yeah.
it's not related, but I just wanted to.
I'm not
ask
sure
why.
the like clearest way, yeah, to motivate this, but just like,
What makes this work?
yeah, it turns out there are various formulas involving like the Wronski map and also like the Grassmannian duality that make this like the correct choice. Yeah, for example, okay, like maybe one thing I can quickly explain is like, okay, how do we get this solution? Like we kind of want to take this polynomial in GR13 and embed it in GR24. And under this thing, how you embed GR13 and GR24 is you just take the integral, the space of antiderivatives of this thing. So the space of antiderivatives of this thing is this thing. And it will have the same Kluger coordinates as this thing.
What's an anti?
Like,
Oh, anti, like in calculus.
yeah.
Sorry.
Yeah, so like this thing is the integral of this thing, and then this thing is the integral of, there's like, the constants. These are the constant functions. Yeah, Tony?
I'm just wondering, just relating those two proofs, I wonder if Cavaliero-Moser could be connection between the two, right? Because that's sort of related to, it's a bidimensional integral system related to KP, and the Gaudet Hamiltonians are related to Cavaliero-Moser. I don't know, just.
Yeah, it's certainly very suggestive. So yeah, it'd be interesting to say something more precise.
So if you generate the rational normal curve, if you change the rational normal curve on Schubert conjecture, you get different solutions to all of the oscillating flags. If you degenerate it into a curve that breaks into pieces, I guess you can't take oscillating flags anymore, but you can take secant flags. But have any idea what happens then? Because it's still possibly true.
No, so there is conjecture called the total reality conjecture for convex curves, which says that you can replace your rational normal curve. So the rational normal curve has the property that any like endpoints are linearly independent, and you're supposed to be able to replace it with any curve with that property. As for other curves, I don't know. It's a good question. Yeah.
Did you use explicitly the Betten's equation from the Scotland model? Do you have it in your, I don't know what it is, I'm curious what it is.
No, I mean, we kind of, like for this thing, we just use literally this formula to derive this, and then, yeah, but yeah, in terms of what goes into, like, we're kind of relying on this result, so I'm not sure of all the ingredients that go into that.
Yeah, if there are no further questions, let's thank Stephen again.
Thank you.